In this talk, I'm going to present my paper entitled, Which Voting Rules Are More Resilient to Coalitional Manipulation? I'll also incorporate results from an earlier paper, Why IRV is So Resilient to Coalitional Manipulation. My name is François Durand from Nokia Bell Labs, France, and I originally presented this talk at the SSCW 2026 conference in Tokyo. We first illustrate coalitional manipulation with the simplest rule, plurality. Here, 35 voters rank A first, then B, then C, then D. 45 rank B first, and two groups of 10 support C and D, respectively. Under plurality, each group votes for its top candidate. So B is the winner with 45 votes. But the 20 voters supporting C and D all prefer A to B. By raising A to the top of their ballots, they can make A win with 55 votes. This is coalitional manipulation. It can be seen as an opportunity for strategic voting, but we prefer to view it as a form of ex post regret. If voters cast their ballot sincerely, then once the result is known, some of them may feel let down by the outcome and wish they had voted differently. Here is the intuition behind our approach. In practice, there is usually a candidate who is stronger than the others. If this candidate is sufficiently strong, then the rule is not coalitionally manipulable. And what counts as sufficiently strong depends on the voting rule, which makes some rules more vulnerable to coalitional manipulation than others. We want the simplest model that captures this intuition. So in this paper, we study a model called perturbed culture. Each voter's preference is drawn independently. With probability theta, they have a fixed preference ranking, A, then B, and so on. With probability 1 minus theta, their ranking is chosen uniformly at random. Strictly speaking, the perturbed culture favors a ranking rather than a candidate, but the top candidate A of that ranking is exactly the strong candidate we have in mind. In the extreme case where the concentration parameter theta equals 1, all the voters prefer A, making the election immune to coalitional manipulation under almost all voting rules. The opposite case, where theta equals 0, corresponds to the classical model of impartial culture, which generates more disorder. Intermediate values of theta capture varying degrees of preference concentration. Let us examine the behavior of plurality under the perturbed culture model. On the x-axis, we plot the concentration parameter theta of the perturbed culture model. The y-axis shows the CM rate for plurality, defined as the probability that a random profile is susceptible to coalitional manipulation. For n equals 1 voter, plurality is not susceptible to coalitional manipulation. As n increases, the curve steepens and takes on a sigmoidal shape. As n tends to infinity, the curve converges to a step function. Thus, there is a phase transition with a critical parameter theta c. For smaller values of theta, plurality is coalitionally manipulable with high probability. For larger values, it is not. Theoretically, we prove that this phase transition occurs at theta equals m minus 2 over 3m minus 2, where m is the number of candidates. Moreover, this convergence is exponentially fast, which means that this limiting result quickly becomes relevant as the number of voters increases. To analyze other rules, we introduce several strengthenings of the notion of Condorcet winner. The first is the pair-safe Condorcet winner, which we illustrate with the Maximin rule. Take the same profile as before, and its matrix of pairwise margins. In Maximin, the score of each candidate is given by its worst pairwise margin. Here, candidate A is the Condorcet winner, hence wins the election. Now imagine that the B voters bury A, sending it to the bottom of their ballots. A's margin against C becomes worse than B's margin against A. Now B is the Maximin winner, hence the manipulation succeeds. Now return to the sincere profile. But imagine that instead of 35 voters, the first group now has 50 voters. Even if the B voters bury A, each of A's margins remains better than B's margin against A, hence B cannot win. The manipulation fails. We say that A is a pair-safe Condorcet winner if the coalition of voters preferring B cannot create a defeat for A that is stronger than B's own defeat against A, and if a similar condition holds for the possible manipulation attempts in favor of C or D. In that case, not only Maximin but also ranked pairs, Schulze, and more surprisingly Young are not coalitionally manipulable. This is only a sufficient condition, not a necessary one. In the perturbed culture, this is shown to imply that for all these rules, the critical concentration is at most 1/7. And we actually prove that this is the exact value. Our second strengthening is the set-safe Condorcet winner, which we illustrate with the Nansen rule. We start from the profile we reached earlier, with 50 voters in the first group, in which we now know that A is a pair-safe Condorcet winner. Nansen iteratively eliminates all candidates whose Borda score is below average, or equivalently whose row sum S is negative. Here, C and D have negative row sums. They are eliminated and the scores of A and B are recomputed. Now B's row sum is negative and A becomes the winner. This was expected since the Nansen rule cannot eliminate the Condorcet winner when one exists. Now imagine that the B voters bury A. This time the row sums of A and D are negative. So both are eliminated, then C is eliminated and B finally wins. The manipulation succeeds. Now return to the sincere profile. But imagine that the first group is raised from 50 to 60 voters. Even if the B voters bury A again, only D is negative now. D is eliminated. Then C is eliminated. Finally, B is eliminated and A wins. This particular manipulation attempt fails. But we could have seen from the start that no manipulation attempt could succeed. For B to win, A would have to be eliminated at some round, which would require visiting a subset of candidates in which all the margins of A's defeats together outweigh its victory against B. This is clearly impossible here. We say that A is a set-safe Condorcet winner if the coalition of voters preferring B cannot make all the margins of A's defeats together outweigh its victory against B, and if a similar condition holds for the possible manipulation attempts in favor of C or D. In that case, Baldwin, Nansen, Kemeny, and simplified Dodgson are not coalitionally manipulable. Again, this is only a sufficient condition, not a necessary one. This is a stronger condition than the pair-safe Condorcet winner. In other words, the set of profiles with a set-safe Condorcet winner is included in those with a pair-safe Condorcet winner. In the perturbed culture, this is shown to imply that for all these rules, the critical concentration is at most m-2 over 4m-5. And we actually prove that this value is exactly the threshold, a result that also holds for the usual Dodgson rule. Our third strengthening is not new to this paper. It is the resistant Condorcet winner, which we illustrate with the black rule. We start from the profile we just reached with 60 voters in the first group, and where we now know that there is a set-safe Condorcet winner. Black elects the Condorcet winner when one exists, and otherwise the candidate with the highest Borda score, or equivalently the highest row sum. Here A is the Condorcet winner, so black elects A. Now imagine that the B voters bury A. A now loses to C and D, so A is no longer a Condorcet winner. Since there is no Condorcet winner, black falls back on the row sum and B wins. The manipulation succeeds. Now return to the sincere profile. But imagine that the first group is raised from 60 to 70 voters. Even if the B voters bury A again, A still beats C and D, so A remains the Condorcet winner. The manipulation fails. We say that a candidate is a resistant Condorcet winner if it stays a Condorcet winner even after any coalition preferring another candidate tries to bury it. In that case, of course, no Condorcet rule is coalitionally manipulable, but this is actually an equivalence. For a given Condorcet rule, it is just a sufficient condition, though. It can be non-manipulable on a profile even when no resistant Condorcet winner exists. This is even stronger than the previous properties. A resistant Condorcet winner is in particular a set-safe one, which is in particular a pair-safe one. In the perturbed culture, this implies that for all Condorcet rules, the critical concentration is at most 1/4. Black, Slater, and Copeland have exactly this value, meaning that they achieve the worst critical concentration parameter that a Condorcet rule can have. Our last notion is the super Condorcet winner, which we illustrate with instant runoff voting. We come back to the original profile of the talk, with only 35 voters in the first group and 100 voters in total. In the full profile, A has more than 1/4 of the votes. In each three-candidate sub-election, A has more than 1/3 of the votes. And in each two-candidate sub-election, A holds more than half of the votes, thus satisfying the classical definition of a Condorcet winner. Altogether, these conditions define a super Condorcet winner, a candidate whose plurality score is above average in any subelection. In that case, IRV and several of its variants are not coalitionally manipulable. Again, this is only a sufficient condition. On our map of notions, the super Condorcet winner lies off the chain. It is logically independent of the other three. In the perturbed culture, for all these rules, the critical concentration is exactly 0. This means that even with minimal preference concentration, they are resilient to coalitional manipulation with high probability. As we did for plurality, let us represent the CM rate as a function of the concentration parameter theta and examine how it evolves with the number of voters n. It helps visualize what the theory predicts. For any positive theta, the limit CM rate is 0. As a side note, what happens precisely for theta equals 0 is covered in a forthcoming IJCI paper with Elie de Panafieux and Guillaume Perarno. In this talk, we mention the critical concentration parameters for rules of the IRV family, the Maximin family, the Baldwin-Nansen family, the Black family, and plurality. Our Amos paper also covered plurality with runoff. In this paper, we also cover Coombs, Buckland, Borda, Kimrausch, and Vito. Let us now compare theory with experiments using the Netflix dataset. On the horizontal axis, the voting rules. On the vertical axis, the empirical CM rate. This dashed line is the measured fraction of profiles without a pair-safe Condorcet winner, which gives an upper bound on the CM rate for all rules in the Maximin family. Similarly, these two dashed lines represent the measured fractions of profiles without a set-safe Condorcet winner and without a resistant Condorcet winner, relevant for the Baldwin-Nansen and the Black families, respectively. This last dashed line represents the measured fraction of profiles without a super Condorcet winner, relevant for the IRV family. It is quite low, meaning that most of the profiles do admit a super Condorcet winner. Finally, here are the measured CM rates. Strikingly, each bar lands almost exactly where its bound predicts, revealing the empirical tightness of these bounds. For the fair vote dataset, the absolute values are different, but the qualitative conclusions remain the same, which confirms their robustness. Now we will examine whether our extremely simple model can nevertheless predict which voting rules are more resilient to coalitional manipulation. For a given number of candidates, here 5 candidates, our perturbed culture analysis yields a value of the critical concentration parameter for each rule. On the horizontal axis, we rank the rules by this theoretical susceptibility to coalitional manipulation. The vertical axis will rank the same rules by their empirical CM rate in the Netflix dataset for the profiles with this number of candidates. If theory and practice agreed perfectly, all dots would lie on the diagonal. We now move each dot to its empirical rank. Overall, the agreement between theory and practice is striking. The main deviations concern Coombs and Buckland and are discussed in the paper. Here again, the corresponding plot for the fair vote dataset confirms the robustness of our results. Thank you for your attention.